This series of videos provide a review of simple regression, or regression with a single predictor variable. Where correlation describes the direction and shape of an association between two variables, regression helps us to predict how someone will perform on some variable, or it can help us to understand why, what factors may be influencing why different people perform or score differently. This can involve attempting to understand or predict all sorts of things: GPA in college, behavior problems, reading ability, based on how someone scores or their value on some other variable like their SAT score or peer behavior ratings, or how much their parent reads to them. To begin, there are a few terms we need to introduce. First is the predictor variable. That's the variable that we are using to predict someone's score on something else. For example, if I'm using student SAT scores to estimate or predict their college GPAs, student SAT scores would be the predictor variable. Now, we typically use the letter X to generically refer to predictor variables when we don't have a specific real-world example. So you'll see X used a lot in some formula. Also, in this set of videos, we'll focus on what's called simple regression. That's where you only have a single predictor variable. If you have more than one predictor variable, you need to perform a multiple regression. I'll make reference to multiple regression from time to time, but we won't cover it here. Finally, I should note that you may also see a predictor variable referred to as an independent variable if the predictor is something that's being manipulated by the researcher. By manipulating the independent variable, I mean that we are choosing values and assigning people those values on it. I can't assign one student an SAT score of 900 and assign another student an SAT score of 1600. So while we may use SAT scores to predict college GPA, technically we should not call it an independent variable. On the other hand, if I'm testing some new math curriculum, I can assign one student into a classroom that gets the new program and assign another student into a classroom that's business as usual. In that case, we can refer to intervention or treatment status, whether they receive the new program or not, as an independent variable. An outcome variable is the variable being predicted by something else. For example, if I'm using student SAT scores to estimate or predict college GPAs, their college GPA would be the outcome variable. We typically use the letter Y to generically refer to an outcome variable when we don't have a specific real-world example, so you'll see Y show up a lot in equations. Now, with the outcome, it's important to note that it must be a continuous variable on an interval or ratio scale. You can't perform this type of regression if the outcome is categorical or dichotomous. Something like predicting whether a student does or does not drop out of high school. That requires a different type of analysis. Also, it's worth noting that you may see the outcome variable referred to as the dependent variable if the predictor is being manipulated by the researcher, if the predictor is an independent variable. Now, you may see people use the terms predictor variable and independent variable interchangeably, and the same applies to outcome variable and dependent variable. I mean, heck, you may even catch me doing it sometimes myself. But technically, they're not the same thing, and it all comes down to whether the independent variable is being manipulated, whether you have a true experiment. But it's important to understand that so that you don't get confused if you see someone refer to high school SAT scores as an independent variable. Just think predictor variable. Now, in order to perform a regression analysis, there obviously has to be some relationship between the two variables, between x and y, just like we see here. It might be the number of hours parents spend reading to their child each week is related to their child's literacy skills. Or it might be high school seniors' SAT scores being related to their college GPA. There has to be some relationship between the two. Now, to simplify the picture, we'll replace the individual points that correspond to the X and Y combination for each person with this ellipse that reflects the overall shape of that distribution. This ellipse reflects all of the actual data for everyone in our sample. Now, the way regression works is that it calculates a line that goes through this ellipse of scores, and this line is used to make predictions for the outcome, y, based on values of the predictor x. Now, technically, what I just described, a line being used for prediction, is for simple regression where we only have one predictor variable. We'll see how this changes when we have more than one predictor variable when we get into multiple regression. Technically, what we're going to learn is called least squares regression, and we'll see why later. But for simplicity, we'll just talk about it as regression and the regression line. Our regression line tells us what score on y we would predict for someone based on their value for x. Once you know the line, you can plug in a value for x, be it hours parent read to their child or a student's high school GPA, and calculate their predicted value on y. Now notice that we're talking about the regression line being the predicted scores. This is important because the regression line or regression equation doesn't tell us what someone's score really is. It tells us what we would predict their score to be based on whatever value they had on x. More on that later. But for now, let's travel back in time to high school geometry and the equation for a line. Different texts will use different notation, but it's always inherently the same thing. You may have seen the regression equation written as y equals mx plus b, or y equals bx plus a, or y equals b0 plus b1 times x, or something else, but it's just different notation. For us, we're going to use the more mathematically sophisticated y equals b0 plus b1 times x. We'll see why that's a better choice when we get to multiple regression. This equation, y equals b0 plus b1 times x, is called the regression equation. For now, let's get rid of the ellipse and the raw data and just focus on the regression equation and what the different values for b tell us. b0 is what's called the y-intercept. It's the predicted score for y, the predicted score on the outcome, when x is equal to 0. This is fairly obvious if we just write the regression equation and then substitute 0 for x. That solves to y equals b0. Again, b0 is the predicted score on y when x equals 0. b1 is the slope of the regression line. It describes the relationship between x and y in terms of how the predicted y changes based on differences in x. Specifically, it's how much the predicted value of y changes with a unit change in x. By unit change in x, I mean whatever units we're measuring x in. For example, if I'm predicting people's weight in kilograms based on their height in centimeters, b1 is the change in their predicted weight if there's a 1 centimeter change in their height. If I'm predicting children's scores on a reading assessment based on how many hours their parent reads to them each week, b1 is the change in predicted reading scores with a 1 hour increase in reading by the parent each week. You can see this if we write the regression equation and then add 1 to our value of x. If we then solve this by multiplying b1 by x plus 1, we see that by adding 1 to x, we end up adding another value of b1 to y. b1 is the change in predicted y scores for a unit change in x. As with other statistical constructs we've discussed, you may see several different but mathematically equivalent formula for calculating B1 and B0. Let's start with the formula for B1, the slope of the regression line. Given the slope of the regression line reflects the association between x and y, it may not be surprising to know that you can calculate the slope based on the correlation coefficient of x and y, along with their standard deviations. Specifically, in simple regression, where we have a single predictor variable, the slope of the regression line B1 is equal to R, the Pearson product moment correlation, times the standard deviation of y divided by the standard deviation of x. Now, if we manipulate this equation a bit, we'll see that we can derive another, more computationally simple formula for B1 that also makes some intuitive sense. First, let's substitute the full formula for the correlation coefficient in place of R on the right-hand side of the equation. Then let's also write out the equation for the standard deviation of y and the standard deviation of x. Now, notice something with the standard deviations. Both have the square root of n minus 1 in their denominator. These will cancel out, leaving us the formula for r times the square root of the sum of squares for y divided by the square root of the sum of squares for x. Now notice we have the square root of the sum of squares for y in both the numerator and the denominator. These will also cancel out, leaving us the sum of x minus x bar times y minus y bar over the square root of the sum of squares of x times the square root of the sum of squares of x. Well, given we have the square root of the sum of squares of x times the square root of the sum of squares of x in the denominator, that solves to just the sum of squares of x. Now, take a look at the numerator. We know what that is. We have another term for it. It's just the sum of the cross products. So B1 is equal to the sum of the cross products divided by the sum of squares for x. In essence, it's just how much x and y vary together divided by how much x varies on its own. The formula for B0, the y-intercept, is equal to the mean for y minus B1 times the mean of x. To see why the formula for the y-intercept is the mean of y minus the slope of x times the mean of x, you have to first understand what's called the point of averages. Whatever the variables, whatever their relationship, the regression line always passes through the mean of x and the mean of y, what we call the point of averages. If you think about it for a moment, that makes intuitive sense. If someone's score on x is exactly at the average for x, what would we expect for their score on y? The average on y. Therefore, if we know that the predicted score at the mean of x is the average for y, and we know that for every unit increase in x, the predicted scores change by the value of b1, by subtracting b1 times the mean of x, I can determine the predicted score when x is equal to 0, which is the y-intercept. Okay, so that's how we calculate regression coefficients in simple regression with a single predictor. In our next video, we'll go through the actual calculations using some survey data. Bye for now.